The eye is made up of many different structures that attribute to vision, but I'll be focusing specifically on the lens and the retina. Problems with the lens and the shape of the eye can cause issues with how light rays focus on the retina, leading to conditions like myopia and hyperopia. In a normal eye, light rays pass through the lens and converge on the retina, producing an image that can be seen clearly. Myopia, also known as nearsightedness, can occur due to a lens that is too strong or an eye that is too long. People who have this condition struggle to see distant objects clearly. Entering light rays converge in front of the retina rather than on it, producing a blurry, unfocused image. Hyperopia, also known as farsightedness, can be thought of as the opposite of myopia. This condition can occur due to a lens that is too weak or an eye that is too short. People who have this condition struggle to see close-up objects clearly. This is because entering light rays are unable to converge enough or fast enough to focus on the retina and instead converge past it, producing a blurry image. Both myopia and hyperopia can be corrected through the use of lenses like eyeglasses or contacts. I'll be using these lasers, some lenses, and this drawing of the eye to show how these problems are corrected. This lens here is a converging lens and will represent the lens of the eye. And this eye is too long, so the distance between the lens and the retina back here is too far. We know this because the point of convergence here is in front of the retina rather than on it. So this person is myopic. This problem has an easy solution, however. We can place a diverging lens in front of the eye, and you can see that the light rays now converge on the retina. A diverging lens is necessary because before, this eye was converging too much, so a diverging lens spreads the rays out and lessens the convergence so that the rays are in the proper place and a clear image can be seen in front of the eye. Someone who is myopic will have eyeglasses that look just like this lens. I'll now show an example of how hyperopia can be corrected. The same converging lens will be used to represent the lens of the eye. This eye is too short, which we can see because the point of convergence is past the retina back here rather than on it. To correct this condition, a converging lens can be placed in front of the eye to help light rays converge more, as they were not converging enough or fast enough before. When we place this lens in front, the rays can converge on the retina and a clear image will be produced. This is what a hyperopic or farsighted person's eyeglasses will look like. Once it is determined whether a person is myopic or hyperopic and shape of the lens, converging or diverging, is chosen, it is necessary to know what power of lens a person's eye requires to fully correct their vision. To determine this, we can use the lens equation. We'll start with an example of myopia. In this example, the far point was determined to be 0.5 meters, and the glasses lenses are 0.02 meters from the eye. The far point is simply the first point at which the eye can no longer focus on a distant object. The lens equation is 1 over dO, which is the distance of the object, plus 1 over di, which is the distance of the image, equals 1 over f, which is the focal length. Because we want to see objects that are far off, we'll say that the object distance is infinity, which allows us to cancel the term 1 over dO. We're left with 1 over di equals 1 over f. To find image distance, we'll need to subtract the distance between the lens and the eye from the far point. Once we have this value, we can input it into the equation and solve for the focal length. In doing so, you can see f equals 0.48 meters. Lastly, we'll take the inverse of this number to convert the units from meters to diopters, which are the units of measure used in optometry when writing a prescription for lenses. So 0.48 meters equals negative 2.08 diopters. This value is negative because f for a diverging lens is always negative. Next, we have an example of a hyperopic person. This person's near point, the first point at which a close-up object can be clearly seen, is 0.2 meters, and the glasses are 0.02 meters away from the eye. The object distance to the lens is 0.1 meters. We need to use a converging lens to produce an image further away from the eye so that it can be seen. We'll first subtract the distance between the eyeglasses and the eye from the near point to obtain DI. Now we can input both DO and DI into the lens equation, where DI is negative because a virtual image is being made. In doing this, you can see we get F equals 0.28 meters and therefore positive 1.25 diopters. As a final way to demonstrate the power of corrective lens necessary to fully correct vision, I'll be finding my own far point as I am a myopic person. I have this post-it note here with the letter A drawn on it, which I'll be pasting to the wall at eye level. I'll start as close to the object as possible, then slowly back away until the object becomes blurry. The distance between my stopping point and the object will be my far point. I'll repeat this process for both eyes. My far point was determined to be 0.508 meters for the left eye and 0.444 meters for the right eye. Using 0.015 meters as an approximate distance between my glasses and my eye, I found the DI to be 0.493 meters on the left and 0.429 meters on the right. Lens power was found to be negative 2.03 diopters, while the right eye was negative 2.33 diopters. My known prescription is negative 2.00 diopters for the left eye and negative 2.25 for the right eye, which is actually pretty close to my calculated values. The most likely reasons these values weren't exactly correct would have been due to not quite stopping at the right point where things become blurry. It can be hard to get that point exactly right. And also not using the correct value for the distance between my glasses and my eye.